Welcome, good afternoon, and thanks also to Dgtronix for the invitation. I will tell you a story. The story starts with an idea. The idea is to design a very high-speed digital connection between two different points. As every idea and every engineer had in his mind, the first thing is to to think about which is the best connection, the best way, the best net design to connect these 2 points. Starting with differential nets. Okay, we can discuss about that. It's one of the best point-to-point connection that we have, but also we need to take into account the space requirement, because most of your application, the PCB board seems to be smaller and smaller and smaller and smaller. Just to remind you, the last talk about the SMI connectors in the last 10 years, it becomes smaller and smaller again. Third point, low crosstalk, and of course also low cost, because your board should be high speed but low cost at the same time. And at the end of the story, we should have also an idea about how to recover the clock and, if necessary, use the equalization process to obtain a very high quality signals at the end of our nets. But let's start with the idea. This more or less should be the layout regarding, for example, a PCI Express connection. And as you know, one of the most important things is to choose the stack-up, of course, the correct material, characterize the correct material, because in most of the cases, the vendors give to you some numbers, but the question is how these numbers are close to the reality. That's another point. Same story, how many vias we should put in the middle across the net to avoid skew, avoid signal degradation, or avoid problems, emission, and at the end of the story, also take care about the back-drilled vias. Is one of the most expensive things that an engineer can do on our own PCB, because of course, it's the last chance. We should reduce the stub, because we need to reduce the noise, we need to reduce the emission, we need to reduce the signal degradation. Okay, the channel length, we can discuss about that, especially in a differential nets. We should avoid different lengths because this generates skew in most of the cases, and this means performance degradation. Last but not least, channel separation and crosstalk. But let's start designing our transition and have an idea about the impact of the vias. We can do easily in advance, just 5 minutes before that we have to think about the new devices or a new connection or a new channel. We can use, of course, a macro to design this directly, but basically we want to investigate which is the best connection between 2 different points using through the vias. Okay, let's have an idea about the topology of our transition. It's a simple macro to generate this kind of geometry automatically, and have a look at the S parameter. Okay, we have put just 2 ground vias. We have put just the transition that coming from the first layout to the third one. More or less, the S parameter could be nice, probably. But this is not the full geometry. This is just a transition. Let's investigate a bit on how the impact of changing the layer from the top to the bottom has an impact in terms of S parameter, degradation, resonance, because this generates problems. And as you know, as I told you in advance, this is the part of the story. We should, we should also take care about the connection. We should take care about the length of the net, the type of the net, and also put all together just to have a complete picture of the problems. More or less, this is a simple block basically is a mathematical implementation of the net that we have inside CST, it's possible to have an idea about the eye diagram and have a look at the difference between changing just the transition from top layer to the second one or top layer to the last one. Okay, changing the layer or backdrilled the vias more or less has an impact, but is negligible. More or less, the performance are the same. But what happens if we change something in the geometry? For example, I will move directly to this slide. If we take care about active model, like IBIS file, SPICE file, IBIS AMI, this has an impact because inside this model you can find a lot of capacitance, extra capacitance, parasitic effects. This has an impact in terms of performance, in terms of transition, and also in terms of eye diagram aperture. We should take care about that. But let's introduce something more. Let's introduce also the net made by using a 3D software simulation, a 3D tool directly, and have a look at more than one net close to each other. This generates problems because at the moment we have analyzed only one transition, only one net, alone, without nothing. Now we have more than one net. And this generates noise. This generates crosstalk. This generates problems that we need to take care of, especially in a very complex board. Same story when we are trying to enforce or try to use a very high-speed net, a high-speed digital communication. But basically, the S parameter, the transition, is not so bad. Also, the eye diagram related to this S parameter more or less can be usable for a very high-speed communication. But we forgot something. We forgot the connectors. And at the connectors, something could be different from what you have in your mind. Especially when instead of the connectors, we just use part of the layout that the layout guy has designed for us. This is a complete net, starting from one side of the connector and ending probably in the middle of the PCB, or close to the active component. As you can see, this generates a resonance, mainly due to the extra capacitance, due to the net, due to the geometry, due to a lot of things, include the IBIS file that we put at the end. But let's increase the complexity. We have designed theoretically the net. We have an idea about the impact of the IBIS file. We have just an idea about the real net. We have just an idea about the connectors. But mainly, and in most of the time, the PCB is connected using some socket, some external connector. Also this generates an impact. Also this has an impact in terms of transmission, S parameters. And of course, also on the eye diagram. Let's have a look at this. We are talking about the same net, just increasing the complexity. Mathematical point of view, move to the 3D, introduce the connectors, introduce some transition, introduce some vias. And at the end of the story, we start there, more or less, but we obtain this one. We should take care. And what happens if we have something like that? Mechanical connector, mechanical socket. Also this generates an impact. We should take care also about that. And the full pictures is something like that. Connectors, IBIS file, some transition, some vias. This is the full picture. And at the end of the story, we are able to evaluate the eye diagram taking care about all the transition that we have. What we can do at this point? We can proceed with the prototyping, with the mass production, or whatever you want, if we are lucky. But if you want to open this eye, because from my side it's not enough, we should move through a new layout first, or in case this new layout cannot be possible because it's just a good trade-off between a lot of requirements that coming from mechanical part, thermal part, and so on, we should introduce what we have called the equalization, emphasis, the emphasis. This is a nice approach to open the eye without change the layout, without change nothing, but just add some mathematical pre-processing and post-processing to the data and open a bit the eye. Also, in CST, it's possible to have an idea about the impact of the equalization because we have some 3 or 4 nice emphasis and de-emphasis process. And at the end of the story, we are able to have an idea about what happened using the first approach, the second approach, or using a better equalization process to reduce the noise and open a bit the eye. That's the end of the story. I hope that could be nice for you, and feel free to ask all the questions that you have. Thank you. Equalization is a mathematical implementation, is just a way to pre-process the data before to sending. Mainly, the equalization process is just to transform the bit that could be sent across the net in a way that consider the degradation of the net can be reconstructed on the other side. It's just a mathematical implementation. The data can be destroyed or, let me say, arranged in a way that can be taken into account the noise across the channel can be easily reconstructed on the other side because from both sides you can find a very strong mathematical implementation behind. For sure, the channel has an impact, but sometimes you cannot change this channel because it's a good trade-off between a lot of things. Okay, I may agree with you that to have a very good quality, good channel quality, you should design better your board. But sometimes it's not possible. It's just a compromise. And take into account this compromise, using pre-processing and post-processing, this is called equalization, you can obtain a very high signal integrity using a low-quality channel, but you should spend more in pre-processing and post-processing. This means you should add more hardware or more microprocessor to do that.